Okay, welcome to EGR 456. In today's class, we will spend most of the time talking about project 6 and how do we solve project 6 problems. Before I begin, I just want to see if there are any questions. Any questions? The rubric for the project 6 is also posted on Canvas. Now, before we jump into project 6, let me quickly recap what is asked and how are we going to do it. Project 6 is based on chapter 6, and we plan to design an autopilot. Now, there are two ways this autopilot needs to be implemented. One is autopilot in the lateral direction and the autopilot in the longitudinal direction. So we talked about this architecture. We talked about the low-level functions of autopilot. We looked at the high-level functions of autopilot. Low-level functions are purely stabilization. High-level functions are path and trajectory planning. We also talked about typical architecture. And then what we said is there are multiple ways an autopilot can be designed. And the one technique that we are going to discuss in detail is called successive loop closure. And the idea is we have a linearized system. So we have a transfer function, and we are going to implement the control on that transfer function. Now, idea is once we have the transfer function, once we implement a feedback loop, once we add a PID, at the end of the day, we try to move poles to the left-hand side of the plane so that the system is asymptotically stable. So that's all we are going to do, but we are going to do that process in a step-by-step fashion. So we are going to look at the innermost loop, then we will go to the step further, and successively we will completely control the open loop system. Now, we talked about this in detail. We talked about the closed loop transfer function. Now, let me go to the crux of what we are going to do. This is an example we talked about. We have a transfer function, and we are going to add a controller so that the poles of the transfer function, they are on the left-hand side of the plane. Now, let's look at how we derive the equations. So first and foremost, the transfer function is used for the linear system. If you look at the equations that we studied on the Genesis block in chapter 5, there were 12 equations. So what we are going to do is somehow we are going to come up with linear approximation of this transfer function. And at this point, I want to take a specific example here. Now, if you want to look at what we have here, this equation results from the Genesis block equations that we talked about in chapter 5. So we did the substitution, we did the simplification, we did the trimming, and finally we got to this equation. Now, the most important part here is this transfer function, and I will highlight this. This transfer function is super duper important. This is the transfer function that we are going to focus. Now, I want you to understand this transfer function. If I write this transfer function, is of the form A phi2 divided by s square plus s a phi1. There is some input, and for the sake of discussion, let me just say my input is delta A, which is the aileron input, and my output is the roll angle. So what this transfer function tells me is the relationship between the roll and aileron. Now, clearly, if I want to find out the poles of this transfer function, so this, let me insert a new slide. So I want you to focus on this equation a little bit more detailed. So for roll dynamics, roll control via aileron. So this is the basic thing that we want to implement. Roll is my output and aileron is my input. And the transfer function, and I just want to say at this point, this is an open loop transfer function. There is delta A and there is phi of s. And this transfer function, if you look at, it is of the form A phi2 divided by s square plus s a phi1. Now, I want you to note a phi2 is a constant. A phi1 is also a constant, and that depends upon the UAV parameters. So if you want to find out what is A phi1 and A phi2, you will have to go back to chapter 5 and look at that big table where A phi1 and A phi2 are defined. So A phi1 and A phi2 are nothing but the constants that correspond to the particular UAV geometry. Now, what we want to do is, first and foremost, we want to compute these values of the constants. Now, I just for clarification, these constants are given on page 69. So if you have a minute, quickly go to page 69 of the textbook and you will see A phi1, A phi2, and D phi2, they are all defined. And finally, this is the transfer function. This is an open loop transfer function. Now, what I want to do is, I want to look at the poles of this open loop transfer function. So if you look at A phi2, this is S plus A phi1. The poles means the denominator of this transfer function is equal to 0, which means I have one pole S is equal to 0, and I have another pole S is equal to minus A phi1. And for stability, we want the poles to be on the left-hand side of the imaginary axis. And depending upon the value of A phi1, clearly right now, one open loop pole is here, and A phi1 could be positive, could be negative, so we don't know where this pole is. So what I want to do is I want to add a controller. And this controller is something like a simple PID control. And this PID control will be A phi 2 divided by S square plus S A phi 1 and phi of S. And then I'm gonna have a loop, something like this. At this point, what type of control we are going to use is not known. So are we going to use K, which is the proportional? Are we going to use KD, which is the derivative? Or we are going to use KI, which is integral? We don't know. But what we know for sure is we want this roll to be stabilized. What it means, if here is what I want to happen. If I give a step input as the aileron command, so if I have on my stick, I give it a step input, then my roll should also show me some sort of step input. I don't want my roll to be oscillating going, or I don't want my roll to become unstable. So I want my output to follow my input. Everybody understood this? Any questions here? Now, this is the simplest architecture. However, if you look at what we have been talking about, you always have, along with the system, you would always have some rates, you're gonna have some disturbances, and so on. So this is called as the basic roll loop. This is the basic roll loop. However, what I want to talk about is just look at the roll attitude control loop. And I'm gonna talk about it using the figure, which is given as figure 6.7. And it is absolutely important for you to refer to this figure. And let me see if this figure is here. So this is the figure that I want you to look at. But there are a lot of stuff, or basically this is the figure that I really want you to look at. So this figure is given on page 100. This is figure 6.7. So at this point, what I want you to do is I want you to think about the implementation. The roll loop that we talked about, the change in the aileron angles or change in the aileron doesn't directly give me a roll angle. What it does, it affects the roll rate. And once that roll rate is integrated, then we get a roll angle. So the idea is the previous loop that we talked about, and I will start with the loop that I had. So I have A phi 2 divided by S plus A phi 1. This loop I'm going to write in a slightly different fashion. So out of this loop comes out P. And once this P is fed into an integrator, what I have is I have the roll angle. So this is the roll rate, and this is the roll angle. And here we have an actuator command. And then what I do is I implement a feedback over here. I implement a feedback over here. And then I have the outermost feedback. I have the outermost feedback over here. Some of you may ask me, and quietly so, why is this implementation needed? This implementation is needed because at the end, what we want is we want a commanded role, and we want to compare that commanded role to the actual role angle. That's why you have this outer loop. So if you look at the way this is, you have integrator here. Then you have delta A. This is the current activation. So the current angle, current aileron activation. So this is actually the roll attitude, hold, control, loop. This is the roll, altitude, control, loop. Right. So now the way what we have done is the input is going to be a commanded roll signal, because here is what you want your autopilot to do. If your autopilot says roll the aircraft by 10 degrees, then somehow this 10 degrees command needs to get translated to appropriate aileron deflection, and that aileron deflection should finally result into the actual roll angle of 10 degrees. Now, this sort of little bit becomes complex when you look at the disturbances. So what happens here is actually you have some additional disturbances flowing in the system. So that's why you add an integrator, which is Ki, and you add 1/s. And then what you do is that guy gets added over here. So let me try to make it cleaner. So this guy gets added over here. Now, what I want you to do here is this is exactly similar to figure 6.9 on page 101. So let's try to identify the knowns and the unknowns. So A phi 2 is known. A phi 1 is known. But the unknowns are Ki, Kp, and Kd. Ki, Kp, and Kd. So the important question here is, how do we find? So the question is this question: how to find Ki, Kp, and Kd? Now, if you look at the textbook, uh, we talked about this in detail. We looked at the different ways of finding out Kp, Ki, and Kd. However, yes, so Alejandro, before you design the autopilot, you have to trim the aircraft, because once you trim the aircraft, this transfer function we obtained from the trimmed aircraft. Because please note, original equations were nonlinear. We trimmed, so we linearized, and we found out this transfer function. So what I'm going to do is, at this point, I'm going to work out the project problem, project 6.1. Then I will explain the course loop, and then I will explain the Sideslip loop, and then I will explain the pitch loop. So at this point, I want you to look at project 6, question 6.1. So I will read the problem. So in project 6, you have to create the PID loops for lateral and longitudinal autopilot. And then in project 7, you have to integrate these autopilots with your UAV simulation. So in project 6.1, it is saying create a MATLAB script that computes the gain for roll altitude hold loop. Assume the maximum aileron deflection, delta A max, because please understand, aileron cannot go through 360 degrees. So your aileron deflection has to be limited to 45 degrees. And then saturation limit is phi max is equal to 15 degrees, and nominal airspeed is 10 meters per second. And use the Simulink file on the website to tune. Unfortunately, if you go to the website, there is no file for this particular implementation. So what I did, I actually emailed you the files that we need to do this exercise. So I'm gonna jump to MATLAB, and here is what we are gonna do. First and foremost, we are going to construct this Simulink diagram in Simulink. Then we will use Simulink tuner to find value of Ki, Kp, and Kd. So saturation limit means this. So even if your command says delta is equal to 1.5, but your delta saturates at 1. So which means even though you are trying to apply the command 1.5, the saturation block, so you supply 1.5, but saturation block is gonna give you 1. If you supply 0.9, saturation block will give you 0.9. So it basically is like a saturation. So it doesn't exceed or it doesn't go below the thresholds. So now what I'm going to do is I am going to the MATLAB, and I will share my screen, and step by step we will find the values for the transfer function. Any questions before I begin? So now you should be seeing my screen, and on the left hand side you should be seeing the description of the project. So once you unzip the project 6 files, you will have all these files. Out of that, I want you to open the file coeff.m. I want you to open the file coeff.m. Everyone got this file? coeff.m. That is the file that I want you to open. Now let me go through what this file does. So this actually, at the end of the day, it finds the value of a phi1, a phi2, a theta 1, a theta 2, a theta 3, a v1, a v2, a v3, a beta 1, and a beta 2. So these are all the coefficients that you need to construct your transfer function. Now, how are these coefficients constructed? These transfer function coefficients, they come from the equation that are given in chapter 5. So I would just point this out. For an example, a phi1 comes from the page that I just gave you a minute ago, page 69. If you look at page 69, equation 5.23, and I will write this down here. So for the reference, this is equation 5.23. Then this equation is equation 5.24. So these equations come from the textbook. Now, we want to find out a phi1, a phi2 corresponding to a particular airframe. So please note, I have just, for the demonstration purposes, I have said jy is equal to 1, mass is equal to 1.5, and gravity is equal to 9.81. But you will have to change these parameters for Zagi. Everyone understood? So your line number 4 will be different. You need to supply jy correspond to Zagi airframe. Then line number 8, 9, and 10. So you will have to find out the values of gamma, gamma 3, and gamma 4 for the Zagi airframe. Everyone understood this? So when you try to run this for your project, especially problem 6.1, you will have to make these changes. Next thing that is important is, please observe, is he's saying that the nominal airspeed is 10 meters per second. So nominal airspeed is nothing but trimming airspeed. So VA trim is equal to 10. VA trim is equal to 10. Everyone understood this? So airspeed has to be 10 meters per second. The next question is, what is the value of angle of attack? To be honest with you, angle of attack value needs to come, this is very important, needs to come from your trim solution. So this needs to come from your trimming solution that you obtained for project 5. Any questions here? So we did trimming for airspeed is equal to 10. So you need to get the value of angle of attack, and Yes, trim for the level flight. This value is the trim for the level flight. And if I recollect correctly, this was very close to 0. Theta trim was trim solution for level flight. Again, theta trim for level flight. The next is, these are the coefficients. And please note, these coefficients I've just implemented from Aerosonde, but you need to change these coefficients. Yes, these values should come from Appendix E for Zagi. You need to change these values from Zagi. So these values I have substituted for Aerosonde, but you need to make sure that you use these values for Zagi. Rho is the density of air, C bar, B, S wing, S prop, K motor, epsilon. All these values must be for Zagi. Any question here? Once you, yes, you can get those values from the previous files that you modified. At the end, what you want to do is you want to find out these values of the transfer function, a phi 1, a phi 2. So what I'm going to do is I'm going to run this script. And after the script is run, I have the value of a underscore phi 1 and a underscore phi 2. Can you see the a phi 1 is 0.39 and a phi 2 is 3.26. Please note, your values will be different once you use your Zagi airframe. Are you with me so far? Any questions here? Next, what I want you to do is, I want you to go to roll loop SLX. You should be able to find this file, roll loop SLX. So double click on roll loop SLX and this file would open. Are you with me so far? Now everybody got this file, Simulink file, a roll underscore loop. Okay, now I want you to take a minute and compare this with the diagram that we drew a minute ago. CC is the commanded role. CC is the commanded role. This commanded role goes all the way to the output because I want to see how well the aircraft performs compared to the commanded role. Then there is this summing junction. Then there is this KP. So this is the value of KP, which is the proportional gain. This is the KP. This is the integral gain, KI. This is the derivative gain. And this is the saturation loop. Can you see that in the saturation loop, there is a delta A max and delta A min? That gives you the upper limit and lower limit on aileron deflection. Then click on this transfer function. And can you see that this transfer function has a numerator coefficient a phi 2 and 1 a phi 1. Then this transfer function gives you the roll rate. this roll rate is integrated. This gives you the roll, and I'm comparing the commanded roll with the actual roll. So this is exactly similar to the diagram that we just drew. But on top of it, I just want to show you here, it just so that I know what is the actual aileron. I have this delta A that shows me the aileron deflection. I'll give you a minute to look at this diagram. And I want you to convince yourself that this Simulink loop, this roll loop, is exactly similar to the loop that we drew. This is the commanded value. And if you command, basically this tells you what type of wave it is. This is the amplitude phi max. So I want this roll to be something like a square wave. And then this is the value of phi max. Then let's find out what are knowns and unknowns. At this point, I know, and I want you to make this change with me. I want you to go to this num and den. And there is a phi 2. What is the value of a phi 2? Your value will be different, but value of a phi 2 is 3.26, which is same as here. 3.26, same as here. A phi 1 is 0.39. So please make these changes. Click OK. Then you have this transfer function. The next part is you want to go and look at the saturation. Here it is saying the saturation is delta max 45 degrees. So I'm going to say my saturation limit is 45 divided by 180 multiplied by pi. So this is, and it doesn't talk about the lowest, but I would just, to be on the safer side, I will say minus 45 divided by 180 multiplied by pi. So I got the saturation block cleared. I got the numerator and denominator block cleared. Now let's see what type of input we want to supply. Here he's saying phi max is 15 degrees. Can you see that in the project? He's saying phi max is 15 degrees. So 15 divided by 180 multiplied by pi. So can you see that this block is not highlighted? This block is not highlighted. This block is not highlighted. At this point, the blocks that are highlighted are Ki, Kp, and Kd. I will give you a minute to catch up. Everybody is with me so far? I missed phi underscore c. So phi underscore c is, this comes from, can you see the step size? The saturation is 15 degrees max. So I just said my amplitude is 15 degrees. Okay. All right. So I got the saturation limit based on the maximum aileron deflection, delta max 45 degrees. So 45 plus 45 and minus 45. Anyone else? Any other questions? So now the only thing that should be highlighted in your Simulink block is roll, Kp, and Ki. So how do you tune this? So there are two ways to do this. We can actually go back to the rules that are given to us. So for an example, Kp is given as omega n square divided by a phi 2. And I want you to go to slide 16 on chapter 6. Slide 16, chapter 6. And Kd phi is given as 2 zeta phi omega n minus a phi 1 divided by a phi 2. Everyone understood? So you can find the values. Okay. This, yeah, just the roll autopilot slide that I just showed. So what, and you can find those values and substitute in here. But here is what should happen. So I'm going to say my Kp value is 1. My derivative value is 0.5. And my integral value is 0.01. And to be honest with you, I'm just guessing. I'm not actually solving this, but I'm just guessing. And what I'm going to do is I'm going to say run. And after I click run, I want you to double click on phi and see what happens. And look at the aileron deflection. And look at the phi value. So what this tells me is this. Initially, my aileron was at 0 degrees, but I sent a command input. Command input is in yellow. And my roll autopilot managed my actual roll deflection to be about the same commanded input. During the step, it kind of lagged behind, but finally it caught up, then went back and it caught up. I want you to run this and see that your actual output in blue is similar to the commanded input. And at this point, I would encourage you to change these values a bit. So say change this to 1.5 and see what happens. And you will notice some things. You will see the ripple, change this value, gain value to 0.9. And now you will observe that the overshoot is gone. Now you can change the integral value, integral gain value 0.5, and see how well the system performs. Not significantly, but as you can see now that your system is behaving similar to the controller or the control input. Let's look at the aileron deflection. Can you see the initially aileron got deflected by minus 20 degrees? Then it went flat and then it flipped. It went maybe to about 35 degrees. It went down and then the aircraft maintained the controlled roll. Any questions here? Were you able to? So this is exactly what is expected in 6.1. If you look at the rubric, I want you to just create this diagram, use the appropriate numbers. Please note, these numbers are not correct. You need to change these numbers for Zagi and find out the values of Kp, Kd, and Ki, either experimentally using trial and error or looking at the equation that is given to us. Before I proceed further, any questions? K's are just the gains, but KD is the derivative gain, KI is the integral gain, and KP is the proportional gain. Everyone got this? Given the difference between slides. You mean the slide version? You mean the slides? Okay, yeah. Yes. Anything else? Now what I want to do is, yes, I'll answer that question in just a second. So now what I'm going to do is, I'm going to go to apps, and here you will have a control system designer. Click on control system designer. So go to app, Simulink app, go to control system designer. There is another app which is called response optimizer. So you can use any of these apps. You can actually use a control system designer, or you can use the response optimizer. So I will show you how you can do it with both. So let me just first start with response optimizer. Or I can start with, let's see, control architecture. Let me see. And there is one more block that I want you to be control system tuner. So these three tools can be used. And I want you to make sure that you have access to response optimizer, control system designer, and control system tuner. Now I'm gonna start with Borna's question. So the question here is there any way to find optimal gain value? So when you say optimal gain value, you want to specify what the optimal is. So what I'm going to do is, I'm going to use the control system tuner, because I already have KI, KP, and KD. So I already have the gains, but these gains may not be optimal. So what I'm going to do is, I'm going to use this control system tuner. And it is interesting. It uses a numerical algorithm, and it's a little bit trial and error. So what you need to do is open control system tuner. Are you with me so far? Control system tuner. Everyone got control system tuner? Okay. Go to tune blocks. This is where you will enter your blocks. Tuning goals. This is where you will enter your tuning goals. Response and design. Okay. So what you will do is, first and foremost, you will actually go ahead and add the update block. Okay. So you will add the blocks. So here, for some reason, it's not, yeah, select, go to tuning, select block, go to tuning, select block, and select tune blocks. So basically, you have to select the blocks that you want to tune. So I want to tune KP, KI, and KD. So I'm going to add blocks. I want to tune KP, KI, and KD and highlight selected blocks. So KD is highlighted, KP is highlighted, and KI is highlighted. So these are the blocks that I want to tune. Are you with me so far? Everybody got these blocks? Click OK. The next thing is tuning goals. So what is the goal? So what is the optimization criteria? So tuning options, I will have to click on the tuning options. So click on the tuning options. And then it actually talks about what type of options you want, what is the tolerance you want, what is the minimum decay rate, maximum natural frequency, and so on. So let's select the goal. Click on the new goal. And as you can see that you can select whatever is your optimization goal. If you want just quick loop tuning, if you want step response tracking, you want rejection, transient, LQR, this is the optimization, LQR, LQG. If you want to add gain limits, overshoot, disturbance rejection, all this stuff. So what I'm going to do is just for the basic, I'm going to say tracking of step command. Everyone with me so far? Tracking of step command. So my goal is I want to track the step input. Now here it's asking me what is my input, and clearly my input is phi underscore C. So add signals to the list, add signal to the list, select signal from the model and create the signal, add signal. So what you need to do is click here, click to the signal that is your step input, and that should get added over here. Then I need to know what is my step response output. Then what I'm going to do is I'm going to find out my output. This should be my final output. So add signal. So now I have roll loop phi underscore roll phi C1, which is this guy. Integrator output of the integrator 1 is this guy. And then you want to specify what type of system that you are anticipating. Are you looking at the first order system? Are you looking at the second order system? Or are you looking at a custom reference model? So on. How to add signals? Go here, add signals to the list, select signal from the model, and then highlight the arrow. Okay, I'll start again. Add signals, select signal from the model. Here is the arrow. Can you see my arrow highlighted in my Simulink block? Zubir, were you able? And then say add signal, and your signal gets added. Click OK, and then it's gonna start tuning, and it gives me the tune response. So this is my desired response. This is my actual response. Now, you may ask me, how do I pick up the gains? And this is going to be a little funny. So I want you to look at the gain here. Can you see my KP is 1.5? My KI is 0.05. And my KD is 0.9. Now, if you want to manage goals, you can actually edit, change the value. So if you try, let's go a step further. Everybody got the first step working? Now what I'm going to do in the next part is, instead of using first order characteristics, I'm going to add second order characteristics. As soon as I add second order characteristics, I can add one more criteria that is called as overshoot. I don't want my overshoot to be greater than 5%. Click OK. And then now you can see the desired response is different compared to the previous goal. And let's see what happens. And then you will see that this response is slightly different than, you can click tune. And then you will see value of KP. You can see now KP has changed to 0.3. KI has changed. KI is almost 0. KD is 0.3. Okay. And then run and see if it actually works. Double click. And as you can see, it's sort of following this step response. And overshoot, please note here, the overshoot is less. So you can actually now change these values. How much is it? 0. KP is 0.30. Okay, KI, KD is 0.30. KI is almost 0. So that is how you can auto tune. But unfortunate part is that there is a delay. So the input is at 10 seconds, but the final response, the steady state response, is achieved at about 13 or 14 seconds. Okay, before I tune it further, I just want to make sure everyone understood what we have done so far. Any questions here? yes, you can play with those parameters and you can actually get this response very, very close. Alternatively, what you can do is go to new goal. You go to new goal and actually do the same thing. You can go to LQR, LQG. You can see the transient response matching, and then same story. You will have to include the inputs. You have to include the output. You can supply what type of initial signal you want, either you want impulse, step, ramp, and then you can, the system or the toolbox will tune the gains for you. So just to clarify, this is what is expected in 6.1 for Zagi. However, there is something else that I want you to think about, which I did not uh, discuss earlier, but now let me make this little bit complex. If you think about it, what we have is, we actually have an external disturbance that is entering into this role model. And I want you to look at figure 6.9 from your textbook. So basically, what you have is you have an external disturbance that is coming in the picture. Now, what do we do with that disturbance? So add library, go to commonly used blocks, delete, add one more summing junction, add one more summing junction, and notice that this summing junction actually only has one positive. This summing junction only has, okay, this summing junction has actually two positives. And there is one more gain, and this gain gets connected over here, and the value of this gain is A phi 2. Value of this gain is A phi 2. So A phi 2 is 3.26. 3.26. And 3.26, and this gain is fed by D phi 2. So what you are doing is you are actually feeding, and this is nothing but the disturbance. So if you look at D phi 2, that D phi 2 is given on page 69. If you look at D phi 2 is given on page 69, and that D phi 2 is comprising of gamma 1 P times Q, gamma 2 Q times R, and all that big expression. So ideally, what you should do is you should add that disturbance over here. But what I want to show here is sometimes you can just model this disturbance as some sort of a white noise. So for example, sources, and you can actually add a white noise, and I'm going to call this as a disturbance. And now let's see if our controller is able to work. So as you can see, noise power is small, and then I'm going to run and then see. Now you see that our controller does not work. At this point, we can actually try to tune it, but you will notice your gains. Now, if you tune it, let's see what is KP. KP has not changed. KI has not changed. KD has not changed. But what I will do now is I will change my goals to rejection of step input disturbances. And what I can do is, again, I can do the same exercise. And then I would say, okay, okay, and then say tune and see. Oh, yeah. Again, it's not able to do what I want to do. But maybe it's giving me some values. So no harm in trying. Just if you want to satisfy your curiosity, what happens? Ki is 0 and Kd is minus 0.11. And then run the simulation and see how well. Yeah, it's working, but not so great. So clearly, the controller is not working well for the input disturbance. And that now needs to be changed. But as far as your project is concerned, you don't need to add disturbances. So basically, you don't, this solution is good enough for project 6.1. Okay. Next part is you want to augment this with the loop for course loop. So what happens when we augment this with the course loop? Once we augment it with the course loop, what we do is we construct figure 6.11. So what we do here is, this is all just phi C. Now what we want to do is we want to construct the course hold loop and construct the Simulink diagram, which is something similar to this, and then tune the KPX and KIX. And I would encourage you to try that. If not, I will explain this on Thursday's class. Next part is Sideslip Loop. So I want you to look at figure 6.13, and I will type it here. So I solved 6.1. 6.1 is solved. For 6.2, repeat the same thing what I did, but for figure 6.11. And for 6.3, repeat for figure 6.13. And for 6.4, you have to repeat the same exercise for the pitch loop. 6. Just a second, Zubir. Figure 6.15. And 6.1 is diagram 6.9. So 6.1 is figure 6.9. Only thing is the disturbance is equal to 0. Okay. So Zubir, the figure that I have in front of me, the figure that we are playing with, it's 6.9. Yes, you can add 0 disturbance. If you really want to be looking at how to tune, then you can add a non-zero disturbance and try to tune the PID gains. But when you have disturbance, external disturbance, you need additional schemes to come up with good PID gains. But you are welcome to add disturbance and then see if your system is working or not. So when you explain, you want to explain how you found the values, what do they mean, and if they are satisfying your design requirements. So essentially what I want you to do is I want you to correlate this result. For an example, you have this result with the actual result. So clearly this result is not matching what I have, because please note my KP, KI, KD values are not good. But as soon as I change my KP, KI, KD values to 1.5, say 0.5, and when I run this, I get fairly decent response. All right, any question about the project or the rubric? If there are no questions, I am going to stop here today and I will do problem 6.2 on Thursday. Well, the right way to do this is look at the guidelines that are given in the textbook. So textbook gives you closed form equations for Kp, Kd, and Ki. What I would recommend you to do is start with those equations. Find the values of Kp and Kd. And those equations are, I will show you, I'll just tell you what those equations are. Those equations are given 6.7 and 6.9. So you would find Kp from 6.7 and Kd from 6.9. Use those values and see how good your response is. And see if your response is acceptable to what you want. If not, you can do the trial and error and see if your response is better than what you get from the equation. And I would encourage you to try this. And if you have any questions, I will answer those questions on Thursday. 6.11 will be the subsystem of Simulink file. 6.11 is the coarse hold outer feedback loop, which means what you need to do is you need to append additional blocks to this loop that you just constructed. You see what I'm saying, Zubir? So to answer your question, Zubir, if you look at the 6.11, 6.11 takes this value, which is phi, and then basically finds out the course heading. So what you want to do is you can add the blocks onto the left as well as on the right side of this Simulink block. Or alternatively, what you can do is you can click this, basically highlight this, and then here you will say create a subsystem. And then this becomes the subsystem, and the coarse hold feedback loop will run outside. So this is like successive loop closure. We stabilize the internal system. So we close the inner loop. Now we will close the heading outside loop. Does it make sense, Zubir? But then there is something else that you want to be clear about, that this becomes an input. So basically, you are going to have ln here. Take it over here. And this is actually going to be an output. And now you will construct the subsystem, because then now what you have is you have the inner subsystem that has the commanded phi and the actual phi. Yes, so they keep on building on the same model, and then you will add kpx, kix, and then you will add additional stuff. Okay, I'm gonna stop recording.